Now let's talk about percentiles. These are measures of location. Percentiles divide the data set up into 100 parts. There are 99 percentiles, and usually the way we denote these is with a capital P and then a subscript that tells us which percentile it is. P1 would be the first percentile, P2 is the second percentile, and so on up to P99. The kth percentile would be P sub k, and this is a value such that k% of the observations are less than or equal to that value. For example, if we look at P sub 2, that's the second percentile, that means that 2% of the data values would be less than or equal to that number. If we look at P98, that would be the value such that 98% of the data values are below that. So we could also think of that 2% of the data values are greater than that value. Here's an example of interpreting a percentile. If you go to graduate school, you may have to take a test called the Graduate Record Examination, or the GRE. The University of Pittsburgh Graduate School of Public Health requires a GRE score no less than the 70th percentile for admission into their human genetics program. If we want to interpret this admissions requirement, one thing we could say is that the 70th percentile is the score such that 70% of the individuals who took the exam scored worse than that. In order to be admitted to this program, an applicant must score as high or higher than 70% of the people who take the GRE. Another way we could think about it is that the individual score must be in the top 30%. And next, let's talk about quartiles. Quartiles are like percentiles in that they divide the data values into equal parts. We have 3 quartiles, and they divide the data set up into equal parts where there's 25% in each. The second quartile is actually the same as the median, because the median, remember, divides our data set into halves. So half of the values are below the median and half of the values are above the median. Here's a data set, and if we figured out the quartiles, the Q1 is 28, the median is halfway between 32 and 33, and Q3 is 38. 25% of the data values are less than or equal to 28, that's Q1. 50% of the data values are less than or equal to 32.5, which is the median. And 75% of the data values are less than or equal to 38, since that's our third quartile. We can also talk about the interquartile range. This is the range for the middle 50% of the data values in a set of data. It's the difference between the third quartile and the first quartile. Here's a picture. We've got our quartiles dividing our data set up into 4 equal parts. The interquartile range just goes from the Q1 up to the Q3. That gives us the middle 50% of the data values. Again, we've got our same list of data values. We've got our quartiles. And our IQR for this would be the difference between the Q3 and the Q1. The IQR would be 10. There's a distance of 10 units between the first quartile and the third quartile. And that range includes 50%, the middle 50% of the data values. When we talk about the 5-number summary, this is actually really simple. It's just a list of 5 numbers. It includes the minimum value in the data, the first quartile, the median, the third quartile, and the maximum value. The reason we talk about the 5-number summary is that we can use that to create a box plot, or sometimes you see this called a box and whisker diagram. This is just a different type of graph of a data set. It consists of a line that starts at the minimum value and goes all the way to the maximum value. It has a box in the middle with lines drawn at the first quartile, the median, and the third quartile. It's going to look something like this. This is a box plot of movie budget amounts. Our minimum was at 4.5. Then we have what we call the whisker that goes to the box. The left line in the box is the first quartile. There's a line in the middle somewhere, that's the median. The right end of the box is the third quartile, and then we have another whisker that goes out to the right to the maximum value. One thing about box plots is that they can also help us determine the shape of a distribution, whether it's skewed right or symmetric or skewed to the left. If we look at this one in the middle, here's a histogram of the data, and this looks pretty well bell-shaped. And if we look at the box plot, notice how symmetric it is. The whiskers are about the same length on each side, and the box is pretty much in the middle between the two. And the median is pretty close to being in the middle of the box. That would tell us that we have an approximately bell-shaped distribution. This distribution is skewed to the right because the tail is longer on the right and most of the data is on the left side. If we look at the box plot, the box is going to be further to the left. Inside of the box, the median is not in the center, it's also further to the left. If we have a distribution that's skewed to the left, that means we have a longer tail on the left in the histogram.
If we were only using the box plot to try to determine the distribution shape, we would want to notice that the whisker on the left is longer, which would mean that there's a longer tail on the left, that the box is further to the right, and also inside the box, the line that represents the median is further to the right instead of being in the middle of the box.
Here's a box plot from a data set that has an approximately bell-shaped or normal distribution. The box is close to being in the center between the two whiskers, and the median is close to being in the center of the box. Here's one from a skewed distribution. Since the box is way over on the left side, that would mean that the right tail is longer, so this one would be skewed to the right. Now, another thing that we talk about with data distributions is outliers. And we've already talked some about extreme values. An outlier is usually an extreme value. It's a value that lies very far away from the vast majority of the other values in a data set. And we can have more than one outlier in a data set. Now, the reason that we're concerned about outliers, for one thing, an outlier can have a dramatic effect on the mean. If we have a value that's very much larger or very much smaller than the other values, it can affect the mean. Remember that the mean isn't resistant. An outlier can also have a dramatic effect on the standard deviation. If we have one value that's very far away from the mean, that means our standard deviation will be much bigger. An outlier can also affect our histogram so that we can't really tell what the distribution looks like. It can affect the scale of the histogram so much.